Today we'll be talking about statistical ensembles. This lecture is a part of the lecture series from the course of Statistical Mechanics, which have the course code of PHY231. In today's lecture, our basic objective is to understand the statistical ensemble. We also need to know the we will solve some problem for the basic understanding of the statistical ensembles. As from the very beginning, we know that in statistical mechanics we are dealing with the behavior of systems with a large number of particles, and as the particles are very huge, so we give up trying to keep track of individual particles. We cannot solve equation of motions or equations for each of the particle involved in their systems. We cannot solve the Schrodinger equation for the all particle involved in that systems. So what you need to do, we have another method of solving it for the, and that is a bit different. So in statistical mechanics handles many particles by calculating the most probable behavior of the system as a whole. So it's a different approach because we cannot reach to each of the particle involved in this system, that because the number of particles are huge. So what we do in statistical mechanics, we calculate the most probable behavior of the systems as a whole, and then we approach to that, rather than by being concerned with the behavior of individual particle that is involved in that particular systems. So in statistical mechanics, basically we assume that the more ways there are to arrange the particles to give a particular distribution of energies, so the more probable that distribution is. So it means if there is the high number of ways in which we can arrange the particles, then this probability of that particular distribution increases correspondingly. We have several examples. Just like the more ways there are to arrange the particles to give a particular distribution of energy, the more probable that distribution is. We have a simple example of 6 energy units and 3 particles to give it. So we have different distribution for it. The particles by itself are distinguishable. Look at their colors are different from each other, so that is why it's distinguishable. And we have 6 energy units and 3 particles to give it. So in this case we can arrange it by 6 different ways, just like 321, 321, 312, 213, and this. In this way we can arrange. So that is why it has 6 microstates. If we look toward this distribution, 2 of the particles are identical and 1 of the particle is different from that. So this is a different distribution, and in this particular sort of a distribution there are 3 ways in which we can arrange the particles, because 2 of the particles are same to each other. And we have another color codes for the energy units. We have this is a simple color coding for these energy units for different colors. So if we look toward this and we compare this distribution, so this has high number of possible ways, so this is the most probable distribution for this case. And here we can see that the distribution function, the color code for this green color is for the blue color is 1, and for this color is 2, and for yellow is 3, and this is correspondingly we have different color for each of them. We have another example that is a very simple example in which we assume all energy distributions are equally probable. This is actually the basic postulate of probability. We had already learned that in the previous classes, that for any particular microstates or for any particular systems, all the probable states, all the possible states are equally probable, and in a very simple ways, the possibility or the probability of all accessible states is equal to each other. We have a simple distribution in where energy is equal to E and the number of particles is equal to 5. Then 3 possible configurations are. The first one configurations are that all the 5 particles are arranged in energy in one level. The second configuration is that the 3 of them are in the 0 energy level, ground state, and 2 of them are in second and third energy level, and the last state is like that 4 of them are in the ground state in the zero energy level, while 1 is at fifth stage. So all the possible configuration have equal probabilities, but the possible number of ways of weight is different for each of these particular systems. We have the dominant configuration of some particular systems where we can do it for large number of molecules and a large number of energy levels. There is a dominant configuration. In the probability distribution, the weight of the dominant configuration is much larger than the weight of the other configurations. So this is like if we look toward this peak, so there is the weight of the dominant configuration is high, so that is why correspondingly its value is higher than other one. And this is what we do, the calculate the factorial terms to do the calculation for that. And the dominant configuration is like that the difference in the W's become larger as n increases, the number of particles increases. And in the molecular system that have molecules almost around 10^23 particles or molecule, then considering the most dominant configuration is certainly have to calculate the averages of that particular systems. So what we do, we can use again the concept of probability, that is actually the basic postulate of probability to deal with these systems. And the basic postulate of probability is that the system is equally likely to be found in any one of its accessible microstates. So if you have many of the microstates are possible, so the possibility for the system to be in any of these microstates is equal to each other. And this is the basic postulate of probability, and it satisfies that given boundary conditions such as the temperature, volume, and the number of particles, it's equally likely to be occurs. We need to solve some problems to best to understand this example and postulate very well. So we need to consider again the orientation of 3 unconstrained and distinguishable spin 1/2 particles, and we need to calculate their probability that 2 are spin up and 1 is spin down at any particular distance. So what will be its probability? So for this purpose of 8 possible spins configuration for these systems, we need to find out all the possible states. Like in the first states, all of the particles, 3 of them will be spin up, and in the second step 2 of them will be spin up, 1 is spin down, that is the last one. And in the third step, the first one is spin up, other is spin down, and the last one is spin up again. And the fourth configuration is first is spin down and the other has to spin up. And coming toward the next configuration, we have 2 of them are spin down and 1 is spin up, and for this we have 3. And similarly at the end we have a simple configuration where all the particles are spin down. So if we look toward the possible state for these particles, which have 2 possibility whether it is spin up or spin down, the possible number of microstates are equal to 10. And if we calculate their probability is equal to each other. So coming toward the problem, that is the problem what we have, that what will be the probability that 2 are spin up and 1 is spin down. So how many states are possible where 2 are spin up and 1 is spin down? We have this system like this one. In this 2 are spin up, 1 is spin down. In this one again 2 are spin up, 1 is spin down. And in this one finally also we have 2 is spin up and 1 is spin down. So the microstates among this 8 in which 2 are spin up and 1 is spin down is 3, and the total possible microstate in this particular configuration is equal to 8. So what will be its probability? It is very easy. Its probability of occurrence of this particular configuration is 3 or 8, because 3 of them have this sort of configuration and the total configuration is 8. So in principle the problem of many particle system is completely deterministics. How we if we specify the many particles wave function of any particular systems, so just like what we do in classical phase space at time t is equal to 0, we can determine psi for all other times t by solving the equation that is actually the time dependent Schrodinger equation, and for that particular case. And if we specify the position momentum of all the particle at time t is equal to 0, we can predict the future behavior of the systems by solving the couple many particles Newton's second law equation of motion for that particular systems. So generally what we do, we usually don't have such a complete specification of the systems available. We need the quantum number f, that is but if we have the particles, that is for that the number of particles of 10 to the 24, what we do, actually we usually are not interested in such a complete microscopic description anyway. Instead we are interested in the prediction of macroscopic properties, and this is a sort of also thermodynamic approach. We use the probability and statistic to calculate the macroscopic properties, and to do this we need the concept of ensemble. And what is a statistical ensemble is actually a large number of and identically prepared systems, and in general these systems of this ensemble will be in different states and thus will have different microscopic properties. And what we do, we ask for the probability that a given macroscopic parameter will have a certain values. So that is actually the goal or the aim of statistical mechanics, to predict any particular probability of the. So we need to solve some problem to further understand this. So for this case what we do, let the system have n is equal to 3 particles, and that is fixed in position, and each with the spin is equal to 1 over 2, and each spin is either up or down. So we have two values for that. When the spin up, it has the value of m is equal to 1 over 2. When the spin is down, it has the value of m is equal to minus 1 over 2. So each particle has a vector magnitude mu, a vector magnetic moment that is called as mu, and the projection of mu along a z-axis is either up or it is down. For spin up, it is up and it has plus mu value, and for spin down, it is down and it has the value of minus mu. So we need to calculate some example on that. So what we need to do, we need to put this system into external magnetic field H. So the classical concept is that a particle with a magnetic field mu in an external magnetic field has energy that is equal to mu dot h minus mu dot h, and r mu h cos theta minus mu h cos theta, where theta is the angle between mu and h. So if we combine the quantum mechanical results, so this tells us that each particle has two possibilities. For one, it has spin up, it will have value of minus mu h, because angle will be equal to 0 and cos 0 is equal to 0. And for spin down, what happen, we will have this angle is equal to 180 degrees, so minus will cancel each other, so we will have mu h value for that. So for 3 particles, the macro state of the systems is specified by specifying m is equal to plus minus 1 over 3, and there are 8 possible microstate for this particular configuration. We have arranged this in the form of a table, and their corresponding total magnetic moment is shown, and total energy is also mentioned here. This is the possible microstate for them. When our positive means spin up, negative means spin down. This is the total magnetic moment, is the summation of individual magnetic moment, and this is the total energy, that is actually the summation of individual energy. In this case, two of them cancel each other, so we have only mu, and even mu h for the energy. And in the the 3 cases, in this case we will have minus mu for these 3 possible configuration, and the corresponding energy is mu h. So at the last case, when all is spin down, we have the energy of minus 3 mu, and the configuration is has the total energy of 3 mu h. So for this is the simple arrangement or the simple example that has been solved. by statistically, and for three particular configurations. So it has equal probability of being found in any one of these 8 states. So what you do, if we have often we have a partial knowledge of these systems, so then the systems can only be in any one of its accessible states that is compatible with our knowledge. So what all these states, I mean, if we have 6 states or 8 states or 10 states depending on the number of particles, so all these states are accessible to this particular systems, and the possibility of accessibility or the possibility of probability of that is equal to each other. So it is important to use all of the information that we have about the systems. So this is the simple problem what we have, and that is gives us the simple explanation of that. And we can arrange this particle like this in the form of so if we increase the number of particles, the microstate will increase, and correspondingly the energy may change, or it will cancel the effect of each other in some cases if we have 4 particles, but in some cases we have the total huge energy. So it is simple. So this problem is further extended toward the 2 other problems what we have, and the basic things what we conclude from this, that if we have 8 possible states for this particular configuration, we can also calculate this by a simple equation, that is 2 to the power n, where n is the number of particles that is involved in that system. In this particular system we have 3 particles, so 2 to the power 3 is equal to 8. So 8 are the possible microstate for this particular configurations. So if we consider that the number of particles is equal to 4, so for that particular case the number of microstate will be 2 to the power 4, and that will be equal to 16. I think it will be equal to 16. So in this case, I mean, if it's very clear that if we increase the number of particles, so the number of microstate increase, correspondingly the value of energy, the value of total magnetic moment and the total energy changes. So for a very simple case, if we have 2 particles, so the possibility for the arrangement of this particle is very simple, because 2 to the power 2 is equal to 4, and that has 4 microstate will be possible in this. 2 of them will be spin up and spin down, and in one case this will be spin up, this will be spin down, and in other case this will be spin down and this will be spin up. So this is the simple configuration for that, where we have the simple case of arranging the particle. So in this case we basically predict the properties. So if we solve another problem here, if we have another problem where we need to calculate and the problem is like that what is the probability that 3 are spin up and 0 is spin down. So how we can calculate the probability for that? Let's come towards the solution of this problem. 3 are spin up and 0 is spin down. Here look at that, how many of configuration we have where we have 3 are spin up and 1 is spin down. This is only 1. So 1 out of 8, so its probability is equal to 1 over 8. In this similar configuration we have another example that is more relevant to that. If we have just like look at that, if we have another example, that is what is the probability that 3 are spin down and 0 is spin up. So what will be the probability? So again, if we calculate the probability of that system, we will come across this possible microstates. If we look toward this 8 microstates, so we have a single particular state like this one. This is the particular states where all of them are spin down and there is no spin up. So if you calculate the probability for this system, how much will be the probability? Definitely it is 1 over 8, so its probability will be like 1 over 8. So the other configuration like 2 are spin down, in this like 2 are spin down and 1 is spin up, 2 are spin down and 1 is spin up, its probability is the same like this case, because we have three particular configuration where one is spin up and two is spin down. So the probability for that particular case will be also 3 or 8, because three of the microstates are in this particular configuration. So this is something about the statistical ensemble, and we have also solved some problem based on that for practicing for the upcoming examination. So thank you very much for now.